Okay, so let's move on to part 2 of this video. And I already talked about the generalized pigeonhole principle. If n pigeons are sitting in k pigeonholes where n is greater than k, then there must be at least one pigeonhole with at least n over k pigeons. Actually, if you think about it, you don't even need this condition, because if n is equal to k, then there must be at least one pigeonhole with at least one pigeon. And even if n is less than k, then n over k is less than 1, still there must be at least one pigeonhole that has a pigeon, so you don't even need n is greater than k here. Okay. All right, so here's his example, and you can draw the picture. 5 pigeons in 2 pigeonholes, then one of the pigeonholes must have at least 5 over 2 or 2.5 pigeons. But since the boxes can't have half pigeons, then one of them must have at least 3 pigeons. Okay. Here's his proof, similar to the one that I gave previously. Assume there's not any pigeonhole with at least n over k pigeons. Then every hole has less than n over k pigeons. The total number of pigeons is less than n over k times the number of holes, which is n over k times k is equal to n. So you see that's pretty much the same thing I did here. I had k holes less than or equal to a, and I showed that the only way to make this happen must be that a must be greater than or equal to n over k. Okay, so it's the same idea. He proved by contradiction, I proved directly. Okay. But you get to the same place. The fact is that n pigeons, k holes, at least n over k pigeons in at least one of the holes. Okay, let's look at some problems from this perspective. Number 2, there are 50 baskets of apples. Each basket contains no more than 24 apples. Show that there are at least 3 baskets containing the same number of apples. Now, this one's kind of tricky. It looks like the pigeonholes should be the baskets and the apples should be the pigeons. But then you have 50 baskets, and each basket contains no more than 24 apples. That really doesn't tell you anything about the number of apples in the baskets. If each basket contains no more than 24 apples, there could be 0 apples in all the baskets. You haven't told the total number of apples or anything. So it seems that we're not going to be able to make this work to make the baskets be the pigeonholes and the apples be the pigeon. Right? So you need to think about this mathematically, that just because something looks like a pigeonhole or ordinarily acts like a pigeonhole doesn't mean it mathematically serves as a pigeonhole in the pigeonhole principle argument. Remember what I said before, that the pigeonholes is the same as the possibilities. When you're looking for pigeonholes in a problem, you want to look at the possibilities. So where are the possibilities specified here? Well, 50 baskets of apples. Each basket contains no more than 24 apples. Those are the possibilities. You could have 0 or 1 or 2, all the way up to 24 apples. There's 25 possibilities for each basket. Each basket could be one of these 25 possibilities. So my number of pigeonholes is going to be, let's see, what number was I using for pigeonholes? Was it n or k? K was the pigeonholes. So my 25 is equal to k. And what are my pigeons? Well, each basket is a pigeon because each basket has to fit in one of these 25 possibilities. Okay. So here's the solution. Again, the difficulty is figuring out what the baskets are, what the pigeons are in this particular problem, and then sorting out the argument as it relates to those baskets and pigeons. So here he says, the baskets are the pigeons. And we place each of them in one of the 24 pigeonholes, which is the number of apples. Okay, so baskets are pigeons, number of apples is pigeonholes. The ratio n over k of pigeons to pigeonholes is 50 over, it should be 25, because you could have 0 apples, but it's still 2. Okay? By the generalized pigeonhole principle, there are at least this many baskets with the same number of apples, so there must be at least 3. All right, so let's look at this again. I showed that the write-up is wrong here. It shouldn't be 2 1/12 because there really are 25 possibilities. I said no more than 24 apples, so that means 0 is a possibility. All right, so here we only get 2. This here must be at least 2. And in fact, you can see that 2 is possible because you could have 0 apples in 2 baskets, then 1 apple in 2 baskets, 2 apples in 2 baskets, 3 apples in 2 baskets, and so on. So so that, in other words, we'd have 25. We'd have each of the numbers 0 to 24 in each of 2 baskets. Okay, so there's a slight mistake here. Be careful about the counting. Seems like he made a little bit of mistake here. Okay. All right, so let's go on to the next one. Show that among any 4 numbers, one can find 2 numbers so that their difference is divisible by 3. Well, let's use the pigeonhole principle. Okay. All right, now here it seems kind of confusing because you're taking about 2 numbers, taking their difference. Where are the pigeonholes? It's clear we have 4 pigeons. But what are the pigeonholes that we're fitting them in? Right. Now, in order to figure out the pigeonholes, let's go back to this idea that you want the difference of 2 numbers is divisible by 3. Difference of 2 numbers is divisible by 3. Okay. Okay. What does that mean? That means if I have 2 numbers, well, here he has it here. If you have n1 minus n2 is going to be equal to 3k. Now, if we do this in mod language, that means that the mod of n1 minus n2, 3, is equal to 0. Another way of saying this would be mod n1, 3 is equal to mod n2, 3, or n1 is equivalent to n2 mod 3. Okay? So what we're saying here is that if 2 numbers, if their difference is divisible by 3, then they are the same mod 3. Okay? So that's the important thing here, is you say the difference divisible by 3. That means that the numbers are equivalent mod 3. Okay, so that's the important fact here. If the difference between the numbers divisible by 3, the numbers must be equivalent mod 3. Now, how many possible mod 3s are there? Remember, mod 3 means you divide by 3 and take the remainder. How many possible remainders are there? Well, the remainders are 0, 1, and 2. Those are the possibilities. 3 possibilities for the remainder. Okay, so in this case, the 4 is the pigeons, and the remainder mod 3 are the pigeonholes. Okay, so let me write it out my way, and we can look at his way also. Okay, so this is problem what? Problem 3. Okay, so I have n equal 4 numbers. Okay, and k is equal to the different possible remainders mod 3. Remainders when divided by 3. Okay, so k is equal to the number of different possible remainders when divided by 3. So it's equal to the number in this set, 0, 1, or 2. So there are 3 possibilities. Okay, so by the pigeonhole principle, that means that there must be at least one possibility. So the possibilities are the remainder, so there must be at least one remainder such that greater than or equal to n over k. In this case, n over k is 4 over 3, which is equal to 1.3. 1.333. There's at least one remainder such that n over k, 1.333 numbers, have that same remainder. Okay. Now, so we have greater than or equal to 1.333. Now we have to have a, the number of numbers must be a whole number. So it's a whole number. So that means that there must be at least one remainder. Must have bigger than or equal to 2 numbers with the same remainder. Okay, so we'll call these numbers n1 and n2. Okay, so what does that mean? So therefore, n1 is equal to 3k1 plus r1 plus r, and n2 is equal to 3k2 plus r. And they have the same remainder. Okay, so then we have n1 minus n2 equals 3k1 plus r minus 3k2 plus r is equal to, well, if you work it out, it's going to be 3 times k1 minus 3k2. So that's equal to 3 times k1 minus k2. Okay, and that tells me that n1 minus n2 is divisible by 3. Okay, so let's do a recap here. What we've said was we have 4 numbers, that's my number of pigeons. We have 3 possible remainders mod 3. So at least 1.33 numbers have the same remainder. Now, since the number of, since it has to be a whole number, we have to have at least 2 numbers with the same remainder. So we did a little algebra here. We called them n1 and n2. We wrote them this way, and we know we can because they have the same remainder. 3 times some integer plus remainder. Did a little algebra and showed that the difference between those numbers is divisible by 3. Okay, so let's compare my proof with his proof. What does he say? Okay, so there are 3 possible remainders when we divide by 3, 0, 1, or 2. So there's your pigeonholes. And since we have 4 numbers, some 2 of them must have the same remainder on division by 3. We can write these 2 numbers. Here he has exactly the same notation that I have. What a coincidence. Okay, then the difference is divisible by 3. Okay. All right, now this is quite an incredible thing, that you choose some numbers and you don't know anything about those numbers. They're arbitrary, but you can choose some 2 of them somewhere and take the difference, and it's divisible by 3. All right, problem 4. This is kind of a generalization of that previous one. Suppose among n plus 1 numbers, you can find 2 numbers such that their difference is divisible by n. Okay, all right, so let's try to apply the same reasoning that we used in the previous problem to this case. Now remember, in the previous problem we had 4 numbers. 4 was the number of pigeons. Now unfortunately he used n here, so maybe I should use capital N for the pigeons. So pigeons, in this case pigeons is what? Pigeons is the number of different numbers. So it's equal to n plus 1. And I'll call that's my capital N, number of pigeons. All right, now what is the number of pigeonholes? Up here we had divisible by 3. When we had divisible by 3, we had 3 possible remainders. Okay, here we're talking about divisible by n. So there are n possible remainders. So my k is going to be equal to the number of remainders. Now my remainders are what? I could have remainders 0, 1, up to n minus 1. How many numbers are in that set? So that's actually equal to n remainders. So please try not to get confused about the new use of n. But just focus on number of pigeons, number of pigeonholes. Number of pigeons here is n plus 1. Number of pigeonholes is n. Okay. All right. So here he says we have n possible remainders and we have n plus 1 numbers. By the pigeonhole principle, at least two of them have to have the same remainder on division by n. So how did he get 2? Remember, here we have pigeonholes. We have pigeons divided by pigeonholes is equal to n plus 1 over n, which is equal to 1 plus 1 over n. Okay. Now, the number has to be an integer, so it has to be bigger than 1 plus 1 over n. So the only possibility is 2. Okay. All right, now from this point on, we write exactly the same, almost exactly the same algebra procedure. If the two have the same remainder, we can write one of them as n times k1 plus r. Remember, here the n replaces the 3, because we're doing it for an arbitrary case. And here we have n2 equals nk2 plus r. The n replaces the 3 again. And here we still again have the same remainder. Do the same algebra and you find out that the difference between these two numbers is n times the integer. So it's divisible by n. Okay, pretty cool proof. Now sometimes they get fancy with this. You have to think a little bit to find the pigeonholes. Look at this one here. Show that for any natural number n, there's a number composed of digits 5 and 0 only and divisible by n. Okay, so let's try to analyze this problem. Where are the pigeons? I don't see any pigeons right off, but I do see pigeonholes. He's talking about division by n. Divisible by n. Okay, so that's going to be my pigeonhole. So my pigeonhole is going to be equal to the remainders mod n. So that's going to be 0, 1, up to n minus 1. Okay. Now the question is, what is my pigeons? Okay. So here's where the cleverness comes in. So let's just read his solution. He writes it out nicely here. So using the previous problem, we're going to find a number divisible by n. Okay. So if we can find any set of n plus 1 numbers, some 2 of them will have a difference that's divisible by n. So we should try to find, and this is the clever part, we should try to find a set of n plus 1 numbers with the property that for any 2 of them, the difference is a number that has digits 5 and 0 only. That's the key. I have to find n plus 1 numbers that has this special property. If we take the difference between 2 of them, the result has only digits 5 and 0. And here's the sequence that he uses. 5, 55, 555, etc. Now, if you take the difference of 2 of these, what's going to happen? Well, you can always take the larger minus the smaller. If you take the larger minus the smaller, you're going to have a bunch of 5s followed by a bunch of 0s. For instance, if I take this one, 5, 5, 5, 5, 5, and subtract 5, 5, 5, you can write down on a piece of paper, you'll find out that you get 5, 5, 0, 0, 0. Okay, so what does that mean? I can clearly get as many numbers as I want that have this form, and the difference between any 2 of them will have only 5s and 0s. So I could take the first n plus 1 of these. As he says here, we can take the first n plus 1 numbers whose only digits are 5. There must be some pair whose difference is composed of only 5s and 0s and divisible by n. Okay, so in this case, the difficulty was find the pigeons. The pigeonholes was very clear. Okay, look at number 6. Given 12 two-digit numbers, so that one can choose 2 of them so that their difference is a 2-digit number with identical first and second digit. Okay, also a little bit of a trick here. In this case, the number of pigeons is clear. We've got 12 pigeons, and we want to fit them into 11 holes. So what are the holes? All right, so here you just do some understanding of divisibility. If a two-digit number has identical first and second digit, that means it's divisible by 11. Okay, so actually this problem is simply looking at the remainders mod 11. And this is the same sort of problem. You have 12 pigeons, 11 holes. Okay, read the write-up. You can see how he does this. All right, so we're going to have 12 numbers. There must be two whose difference is divisible by 11. Okay, and the difference can have more than two digits, and so it must have. Well, if it's divisible by 11 and it has no more than two digits, then it must have the same first and second digit. Okay, it's not possible to have a three-digit number that's the difference of two digit numbers. Okay, now here's a different kind of problem, a geometrical problem. Suppose there are 5 points inside an equilateral triangle of side of length 2. So at least two of the points are within a unit distance of each other. Okay, 5 points inside of the equilateral triangle. So first thing you should be thinking about, let me draw a picture to show what's going on. Okay, I guess I'll go over to my, I'll either go over, why don't I do it down here? So this is problem 5. Just draw it down here. Oops, sorry. And you've got an equilateral triangle, and the sides are of length 2. And you've got 5 points in here. And you want to show that at least two of them are within a unit distance of each other. Okay, so it looks like my points are my pigeons. Now, what are the pigeonholes? Well, let's create some pigeonholes. Now, since we have 5 points, we probably want 4 pigeonholes, and here we can make 4 pigeonholes like this. Okay. Now, if I divide the triangle like this, each one of these smaller lengths has side 1. Okay. What are my 4 pigeonholes? My 4 pigeonholes are the smaller triangles. What can I conclude by the pigeonhole principle? There must be at least 2 points in one of the triangles. Now, if they're in one of the triangles, how far apart are they? Well, you can circumscribe a circle around this triangle, so these 2 points must be within distance 1 of each other. Well, so we must have 2 points in one triangle. So how far apart could they be? Well, if you draw any point in this triangle, and you draw a circle of radius 1 around that point, it's going to contain the entire triangle. For instance, if I start here and I draw a circle of radius 1, it's going to contain all the points in the triangle. What does that mean? That means that every point in the triangle is within a distance 1 of any other point of the triangle. Okay, so if I have 2 points in the triangle, they're within a distance 1 of each other. Let's look at the write-up and see how he says it. Draw a smaller equilateral triangle inside the first one by connecting the midpoints of its sides. This divides the triangle into 4 equilateral triangles of side length 1. Should be a 1 here. Okay, since there are 5 points by the PHP, some 2 points must lie in the same smaller triangle. But these 2 points are in an equilateral triangle of side length 1, so they're within 1 unit distance of each other. Okay. See, he's kind of sparse on this last argument. I might say a little bit more here, and like for instance, you might say, since any circle of radius 1 centered in the small triangle contains the entire triangle, contains the small triangle. Okay. All right. One more geometrical proof that's a similar flavor. there are 10 possibly overlapping small line segments marked on a bigger line segment of length 1. If we add up the lengths of the marked segments, we get 1.1. So at least 2 of the marked segments have a common point. All right, now you can think about this. You have a line segment of length 1. And we can just call this point 0 and 1. And you've got a bunch of small sticks that you want to lay inside here. Okay, so you want to lay them all inside end to end so that they don't overlap. It's not possible because the total length is 1.1. How can you fit them inside? They're too big. All right, so how do we write this up? Assuming to the contrary segments do not overlap, then the total length covered by them is the sum of their individual lengths, which is 1.1. But this is impossible since they're contained in a segment of length 1. So our assumption to the contrary must be false, meaning the segments do overlap. So he's using a proof by contradiction. Okay. All right, last one. There are 13 squares of side 1 positioned inside a circle of radius 2. So at least 2 of the squares have a common point. Now, you don't really have pigeonholes in this example. What you do have is a limited resource. I could call this a limited resource. In the previous problem, the limited resource was length. You only had so much total length that you had to divide among the other segments. In this case, we can talk about the limited resource. In this case, is area. We have a limited area, which is limited by the area of the circle. These 13 squares are inside this circle of radius 2. So the total area is less than or equal to, since it's radius 2, it's pi r squared, so that's 4 pi. Okay. Now, what's 4 pi? Well, 4 pi is less than 13. 13 squares have total area of 13. There must be some overlap because there's not enough room to fit all the squares into this limited area. Okay. So here's how he writes it up. I think this is a nice write-up. So if no 2 of the squares have a common point, he proves by contradiction. So I would say the contradiction, you're going to assume the contrary, that they have no common point. Assume the contrary, they have no common point. So if no 2 squares have a common point, then the total area of the cover is equal to the sum of the individual areas, which is 13. On the other hand, a circle of radius 2 has an area of less than 13, so it's impossible for the squares to cover an area of 13. So some 2 of them must share a common point. Okay. Notice this contradictory structure here. It's not written out all the details, but that's what's going on here. He's doing contradiction. He's saying that contrary to what we want to prove, we assume that there are no common points in any of the squares. The consequence of that is that they cover an area of 13. However, they're inside the circle. The circle has total area less than 13. There's not enough room for them all to fit without overlapping. Okay, so that's the solution to this problem. And there